carbon nanotubes, CNTs are hollow tube-like structures with nanometer scale dimensions. These carbon nanotubes have remarkable features like great elasticity, low density, excellent thermal and electrical conductivity, and chemical inertness. With the help of carbon nanoparticles, researchers continue to make significant breakthroughs in electronics, optics, medicine, water treatment, and other fields. Carbon nanotubes are classified as single-walled carbon nanotubes, SWCNTs, double-walled carbon nanotubes, DWCNTs, or multi-walled carbon nanotubes, based on the number of carbon layers, MWCNTs. This video addresses the latest developments in carbon nanotubes regarding structural enhancements and application advancements. Individual defect-free carbon nanotubes can exhibit extraordinary mechanical, thermal, and electrical properties, leading to conjecture about a wide range of applications. However, difficulties in producing large amounts of pure nanotubes and the need for tubes of only one type in various applications have limited their widespread use. The development of a revolutionary carbon nanotube structure has progressed. New electronic devices necessitate sophisticated technology that can aid in the construction of devices that are smaller in size and have the most functionality incorporated. Only structural development can allow for these kinds of technological improvements. Researchers are still looking at new materials, modifying their structural arrangements, and learning more about how they work. For example, van der Waals heterostructures are structures made up of two-dimensional crystals arranged in layers. Professor Maruyama, Associate Professor Rong Zhang, and their colleagues at the University of Tokyo devised a new method for producing carbon nanotubes. Carbon nanotubes are bound together in a high-temperature environment containing boron nitride to form an even and continuous layer or crystal. Then, using the same method as before, the third layer of molybdenum disulfide is applied. A coaxial structure is a tube structure in which numerous one-dimensional systems are organized on an axis. According to Maruyama, Zhang, and their colleagues, these one-dimensional van der Waals structures constitute a whole new class of material with undiscovered features. They believe their discovery could be helpful in lasers, flexible electronics, electrocatalytic water, splitting to make hydrogen, solar energy conversion, photoelectric devices, and other applications. Carbon nanotubes for nervous tissue regeneration. Carbon nanotubes and nerve cells have a lot of structural and physical similarities. Carbon nanotubes have morphological and dimensional similarities to neurites and dendrites. The charge, roughness, polarity, and chemical structure of carbon nanotubes have the power to change the affinity of neurons bound to the carbon nanotube-containing surface. They are valuable tools for researching neurological diseases and nerve tissue injury because of their unique properties. Biofunctionalized carbon nanotubes. The first method involves injecting carbon nanotubes directly into the nerve tissue. In this technique, carbon structures interact directly with neuronal culture, expanding or dispersing within the cells. Carbon nanotubes are used as adjusters of other materials in a second way, ultimately boosting numerous brain functions. This method can also increase the role of medicinal medicines and proteins, neurotrophic factors, and nucleic acids like cRNA. Peripheral nerve transected sciatic nerve injuries are the most prevalent of many types of neural damage. The intensity of the injury primarily determines the degree to which this nerve regenerates. Scientists have come up with a carbon nanotube interfaced phosphate glass microfiber scaffold for the regeneration of the transected sciatic nerve, which is a recent breakthrough. The transition of carbon nanotube transistors from the laboratory to the commercial market. Carbon nanotube field effect transistors, or CNFETs, were previously only available in the artisanal market, where they were made in very tiny quantities in academic laboratories. Scientists showed how CNFETs might be made in more significant amounts on 200mm wafers in a recent Nature Electronics journal, describing it as an energy-efficient alternative to silicon field effect transistors. The deposition technique for carbon nanotubes used to manufacture CNFETs was evaluated and refined by Max Schuelacher, Assistant Professor of Electrical Engineering and Computer Science at MIT, and his colleagues. This novel approach has the potential to raise production numbers while simultaneously lowering costs. Incubation is a method of depositing nanotubes in which a wafer is immersed in a bath of nanotubes until the nanotubes bind to the wafer's surface. The best performance comes from a perfect alignment of nanotubes in a CNFET. However, aligning billions of 1 nanometer diameter nanotubes in exact alignment across a 200 mm chip is exceptionally challenging. Even though the incubation approach is viable for industry, it fails to align nanotubes well, which was previously regarded as a critical prerequisite for CNFET's performance. Researchers later confirmed that making CNFET utilizing a simple incubation procedure might result in a transistor with better performance than a silicon-based transistor.